And hey, I'm Özgün. I'm the CTO at Citus Data, and I'm excited to be here. Today, I'm going to talk about what we learned over the years in turning Postgres into a distributed database. And some of these lessons are also applicable in a broader context than just Postgres or relational databases. I have about 45 slides, and this is a fairly technical talk. So if you have questions, please ask them. And before I start, I also have a quick question for you. How many of you are familiar with or have worked with Postgres? Actually, awesome. Almost everyone. And then before we start, I'll share with you just 5 slides to introduce the context behind my talk. What is Citus? Why am I here presenting this talk? And what can you expect to get out of this talk? The answer to all these questions is a rock-solid relational database, Postgres. This diagram here shows job posting trends over time on Hacker News. And as of last year, Postgres is as popular as the next 4 databases combined on these job postings. And it's worth learning more about the technical components that make up Postgres and how one goes about scaling them. So slide 1, developers love Postgres. I'm Özgün, the CTO at Citus Data. Previously, I worked on distributed systems at Amazon.com, and I love Postgres too. Our team also loves Postgres, and at Citus Data, we focus on scaling out Postgres and, to Wes's point, making sharding simple, so you can focus on your application and not worry about your database. At Citus Data, every single engineer on the team shares the same mission: to make it so that you never have to worry about scaling your database again. And if you aren't familiar with Citus, if this is the first time you're hearing it, there are just a few things to know before we dive into the challenges of distributing Postgres. 1, Citus is a distributed database that horizontally scales Postgres across multiple machines using sharding and replication behind the covers. Citus's query engine routes and parallelizes SQL queries across the machines in the cluster. 2, we package Citus as an extension. These extension APIs are new and unique to Postgres, and more on them later in this talk. And Citus is available in 3 ways. First, as open source. Second, as a fully managed database service on AWS. And third, as enterprise software. And finally, here's a simplified architectural diagram of Citus. We have a coordinator node here and worker nodes here. These are regular PostgreSQL databases that have the Citus extension loaded. The user or the application connects to and interacts with the coordinator node. This is where you create your table and then say distribute table. When you run a query against this coordinator node, basically you use your standard PostgreSQL library or your tools, and then the coordinator transforms that particular query into smaller queries, pushes them to the worker nodes, gets the results back, merges them, and gives them back to your application. So very simple. There is no data, usually not much data captured on the coordinator node, so it only coordinates work. And each worker node in here captures the actual data as small sharded tables. So one shard is equal to one table, one Postgres table, but all of this is invisible to you. So that previous diagram looks pretty simple, but scaling out SQL is actually an extremely challenging task. And then this talk presentation talks about 3 different challenges that relate to scaling Postgres. Since these are related but different topics, one way to think of this presentation is as 3 separate, shorter talks. This way, if you're super bored during the talk, you just have to wait it out for another 5 minutes or so, and then we'll be talking about something completely different. In my first talk, I'm going to describe replication and high availability techniques in Postgres. In my second talk, let's say you decided to build a distributed relational database. Do you build one from scratch, or do you fork an existing database? Then I'll dive into one of the baddest, meanest problems with scaling relational databases, distributed transactions. And I'm going to conclude the talk. With that, let's switch gears to our first lightning talk. This talk describes the most asked question about Postgres. How do you handle replication and machine failures? What challenges do you run into when setting up highly available Postgres clusters? The typical approach to replication in relational databases is the following. You have one primary node, all your writes go to that primary node, and the primary node applies the changes there, and then it takes those changes and then pushes them, or the secondary nodes pull them to the secondary nodes, one or more secondary nodes. And in the context of Postgres, this setup brings two challenges for applications for clients. First, many Postgres clients are implemented to talk to a single endpoint. So in this setup, when your primary node fails, most Postgres clients will keep retrying that endpoint, that IP or that hostname. Second, Postgres replicates its entire state. So when you're replicating that much state, it becomes hard to shoot different nodes in the head or bring up new nodes in the cluster, into the cluster. Going back to the first problem, to reiterate on that first problem, the issue here is that Postgres has a massive ecosystem of clients. And some of these clients are smarter. For example, the Java client, the JDBC client, can see a failure and retry a different endpoint. However, when we're solving this problem for the masses, for everyone, you need to rely on networking primitives. So this networking primitive could be an elastic IP, or DNS, or a load balancer, or this could be services in Kubernetes deployments. And here in this example, we have our application in here. This could be Ruby, this could be Python, and then it's talking to this endpoint, which is an elastic IP. When the primary node fails, the monitoring agent in here promotes the secondary, detaches the elastic IP from the primary, reattaches it to the secondary. So this way, this application doesn't need to change the endpoint it's talking to, or you don't need to implement application level logic. Everything just happens magically for your Postgres client. The second problem isn't as widely recognized as a problem. So most people, and I used to think this too, that when you have this simple primary, secondary architecture, there is one way to solve a problem, right? Because there is only a primary and there are multiple secondaries. But in practice, if you look at Postgres deployments out there, on-prem, on RDS, on Heroku, they end up following one of three approaches for replication and failover. And there's an easy way to identify the approach they're following. Let's say you add a brand new secondary node into your cluster. How do you reconstruct that secondary node's state? So the first approach is the most common and the most typical one. You have one primary node, and this primary node has the tables data in here and the write-ahead logs. Out of curiosity, how many people in here have heard of write-ahead logs or WAL logs in Postgres? Okay, about a third. So this WAL log, write-ahead log, is basically, you have Postgres. When you modify a row in Postgres, the change first gets committed to an append-only redo log, so that if Postgres were to crash, you can replay the changes from the log. And then in this example, this actually captures all the changes to your database. And the WAL log gets streamed over to a secondary node. And then the secondary node actually replays the changes from the write-ahead logs. And in this first approach, when you build a new secondary node, let's say you brought up a very new secondary node, this secondary node needs to replay the entire state the primary captures from the beginning of time, and now so it can reconstruct that state. And of course, when you're bringing a new secondary node, this operation introduces a significant load on your primary. And this load becomes even more important if your primary is under heavy load, which is when you want to bring up these secondary nodes. And also in this first approach, in the simple approach, you can use local disks or attach persistent volumes to your instances. In this diagram, I'm using local disks because that's the more typical setup. The second approach relies on disk mirroring, or you can think of it as file system replication. In this approach, where your changes get synchronously written to a persistent volume, And then this volume synchronously gets mirrored to another volume. And the nice thing about this file system replication approach is that it works for all relational databases. You can use it for MySQL, PostgreSQL, Oracle, or SQL Server. However, this approach requires that you replicate both your table data and write-ahead log data. And further, each write that you do here on the primary gets replicated synchronously over the network. So you can't even miss a single byte here because file system doesn't know about the underlying data. If you were to miss a few bytes, your database would go in a corrupt state. And the third approach turns the replication and disaster recovery process inside out. So you write your writes to the primary node. The primary node does a full backup every day and incremental backups every 60 seconds to here, this cloud, and here. And your secondary usually follows the primary node, except when you introduce a new secondary node in here, it reconstructs its entire state from S3 or from the blob storage engine here. So this way, you don't introduce any additional load on the primary database. You can bring up a new secondary and reconstruct it entirely from S3. And when the secondary is close enough to the primary, you can start streaming from the primary and catch up with it. So this design itself lends itself more to a cloud-based architecture because you can bring up or shoot down secondary nodes at will. And you can also use synchronous or asynchronous replication because you're capturing the changes in these append-only logs. I'll take a quick pause here. Any questions about the previous 3 slides or the 3 approaches? I'll take a quick poll. Does it make sense? Do these 3 approaches generally make sense? Okay, cool. And here's a simple table that compares these approaches to each other. And for each approach, you can think of its benefits column as the drawbacks of the other approaches. Simple streaming replication is the most common approach. Most on-prem deployments follow this approach. It's trivial, it's easy to set up. Further, if you are using local disks, you can store tens of terabytes of data. Comparatively, the disk mirroring approach abstracts away the storage layer from the database. In this approach, when you lose an instance, you don't lose your ephemeral disk with it. This approach works with MySQL, Postgres, Oracle, which is great if you're a cloud vendor, such as AWS. And in the third method, when you add a new machine, you reconstruct that machine straight from write-ahead logs. And since you're treating your write-ahead logs as a first-class citizen, certain features become trivial. For example, let's say you wanted to performance test your application against your production data, but not against your production database. In the third approach, you can easily take a fork of your cluster because these are WAL logs living in S3, and then you can run your application against that production data and then shut it down at will. So oops, interesting. Let me escape and try this again. Awesome, we're back. So in summary, Postgres comes with 3 replication methods. If you rely on the storage layer, or S3, when reconstructing a secondary node, you can easily bring up or shoot down databases. So that's the cloud-native part of it. This is because your secondary reconstruction isn't introducing load on your primary database. And it's worth noting that all 3 replication methods that I described replicate a database's state in full. And this is also one of the benefits of sharding. When you shard your database, the state you need to replicate per machine becomes smaller. So replication becomes a much easier problem to solve. With this, I'll conclude our first talk. And this brings us to our second talk. Let's say we decided to shard our relational database. And when you think of sharding a relational database, you're talking about taking diverse features built over, in Postgres, in the case of Postgres, 20 years, making all of those features distributed. So how do you go about this? At a high level, there were 3 ways to build a distributed database. One build a distributed database from scratch. 2, you take a widely used relational database and you put a middleware layer in front of it. This middleware layer usually routes queries, such as simple inserts or lookup queries, to the underlying sharded database. And 3, you fork an open source database and make it distributed. And the fork database supports the original database's features as of the time of the fork, and usually it diverges over time, and in essence becomes a separate project. So which one of these approaches would you pick? When we started working on Citus, we said, okay, let's ask around and see what type of queries people send to their databases. So my co-founder, Umur, started forwarding example queries in email threads. And then, this is very early. We're just getting into the world of Postgres. And one day, Umur forwards me this query block, and I'm reading through this thing. And then, okay, there's a transaction here, there's a sequence here, there's a join here, there's a returning here. And then there is this thing called save points. I open up the Postgres manual, and it turns out Postgres also supports nested transactions. So you can create a bookmark in your transaction and roll back to a particular bookmark within that transaction if you'd like to. And I'm like thinking, man, where does Umur find these queries? And this was a week or so after he went to Burning Man, so I'm thinking if he's imagined this thing or something, because if you look at the query doesn't even make any sense. Like at the end of the query, the entire transaction is rolled back. So we debate a little if we should even support this type of nested transaction blocks. And I'm like, I'm fine. I'd like to meet the genius who wrote this transaction block anyway. Let's go and meet them. So we go and meet this company. And it turns out there was no genius at this company who wrote this transaction block. This was a Rails testing framework that auto-generated this query. And at that point, one thing became quite apparent. If we wanted to scale out Postgres, we had to go all in. For a Postgres user, all of the features they rely on need to linearly scale. This includes current and new features, clients, ORMs, and hundreds of tools built around Postgres. So we went ahead and forked Postgres with style. What does it mean to fork with style? If you look at Postgres, and this is an architecture diagram from Postgres 9.0, it has a fairly modular and extensible architecture. In here, you can hook into any module, change or extend its behavior without making a mess. And the diagram shows the different modules within Postgres. For example, if you wanted to distribute the create index command, so you can push it in parallel across all your shards, you hook into this DDL and utility processing module. And the most complex boxes in this diagram are the query planner and executor. Don't be fooled that they look like these nice little boxes. They're actually fairly complex. And then they were at the time highly coupled, and they made assumptions actually about these little boxes underneath, which represent the storage layer. So we decided, okay, this is the hardest part, and we created a two-stage query planner and executor. What does that mean? That means once Postgres parses and semantically validates the query, Citus checks if the query touches distributed tables. If it does, Citus uses distributed table metadata to plan the query for distributed query execution. During the planning step, Citus plans to minimize network I/O and transforms the query into smaller query fragments. Citus then deparses these query fragments back into SQL and then sends them to workers as SQL. Why convert query fragments back to SQL? 2 reasons. First, this way we can decouple the distributed query planner from the distributed query executor and test the planner and executor separately. So if you're writing regression tests, you can enable logging and check that the generated queries that we send between the coordinator and worker are what we expect them to be. Second, once we create these smaller SQL query fragments and ship them to worker nodes, Postgres there can apply its own query optimization and optimize that query for local execution. So I'll make this concrete. Here is a simple example. The application here issues a select query to the coordinator, and the coordinator parses the query. This is Postgres. At that point, Citus kicks in, transforms the parsed query into query fragments, which in this example are different. So we're taking the query and then transforming it into its commutative form. And then we take that query fragments, those query fragments, deparse them back into SQL, send them to worker nodes. The worker nodes do their own planning, send the results back to the coordinator. The coordinator does the final computation and gives them back to the application. And we were quite happy with how we forked Postgres. What made things even better was that Postgres then made these APIs official with an extension framework. So we unforked from Postgres and made Citus an official extension. How many of you have heard of PostgreSQL's extension APIs? Okay, about a fifth or a sixth. So in Postgres, an extension is a shared library that gets dynamically loaded into Postgres' address space. And then this way, the user can start up Postgres and just type create extension Citus. And voila, in the case of Citus, your favorite relational database becomes a distributed database. And before I conclude, let's see if this is going to work. Okay. This is a bit cut off, but then I wanted to show you the initialization logic, how you hook into Postgres' extension modules. This is from Citus, the GitHub project. We're basically initializing ourselves in the dynamic memory segment, so there are a bunch of checks in here. Once we did that, we say, okay, we need a few extra directories, so we tell Postgres, hey, create these directories for us. We register our configuration variables with the PostgreSQL config subsystem. We intercept the planner. We do intercept the executor at a different place, but then we intercept that utility hook. This is the DDL logic. So we basically say, hey, hook me into the DDL logic. We do a bunch of other planner hooks. We hook the logging engine, so that when you error out, we can also clean up our resources. We initialize background worker processes. So these are things that we spawn along with Postgres, and then that does background work. We initialize the transaction sub-engine, like we hook into the transaction and the connection management module, and then we do one final check, and then we have done the initialization. And obviously, all of these function calls are fairly involved, and they hook into PostgreSQL's internals. Okay, awesome, we're back. Any questions up to this point? All right, with that, I'll conclude our second talk on using PostgreSQL's extension APIs. And let's dive into our third talk, handling distributed transactions in a relational database. So distributed transactions is one of the meanest, baddest problems in databases. You do a begin transaction, insert and an update, and once you run a select, you should see your changes applied against the database, but others shouldn't until you do a commit. Or you do a rollback, and your changes should disappear forever. And there are two challenges associated with running distributed transactions. These challenges are like two sides of a coin. The first challenge is, how do you handle consistency in distributed databases? What happens when you're doing a transaction and one or multiple machines that participate in that transaction fail? Consistency is a well-established problem in distributed systems. Three popular algorithms in this space include 2PC, Paxos, and Raft, and the variants of these algorithms. And the primary difference between 2PC there and Paxos from a practical standpoint is 2PC needs all participating nodes to be available to progress, whereas in Paxos, you can get away with a quorum. And in Citus, we looked both into 2PC, that's built into Postgres. Actually, Postgres comes with 2PC. And then we also deployed an experimental expansion called PG Paxos. And we decided to go with 2PC because it has been widely used in production across PostgreSQL deployments. And also, Citus uses streaming replication, if you remember the first talk. So when a node becomes unavailable, its secondary usually gets promoted within a minute. So since the consistency challenge is widely accepted and discussed, I won't dive deeper into it in this talk. Instead, I'll talk about a lesser recognized, but just as important problem for relational databases. Let's say you have a complex transaction block that modifies multiple rows, which is in here, and actually I have 4 of them. What happens when you have them concurrently, running concurrently, and then they modify the same rows in distributed tables, but in different orders? It turns out that one of the trickiest things we need to deal with is a very simple thing. It's very important to databases, namely locks. A lock protects concurrent access to the same data. In other words, a lock prevents two transactions from modifying the same row at the same time. But in databases, transactions can be quite complicated. They can grab many different locks, and at some point, they could end up waiting on each other. That's known as a deadlock. This is a very bad situation that needs to be dealt with. Otherwise, you cannot reliably run your database. So let's zoom in a bit on where and when you run into locks in PostgreSQL. Well, there's many different cases, but pretty much any command that you run grabs some locks. But an important example is the row level lock. If you update a row in Postgres, that update in here grabs a lock, and any concurrent transaction that tries to update the same row will then block until the first transaction is finished, which means either when the first transaction commits or aborts. So the left-hand side is the first transaction, the right-hand side is the second one. And then after the commit or abort, all locks are released, and the second transaction can continue. Now, if two transactions don't modify the same row because their filters aren't conflicting, they can run concurrently. And this is a very nice thing about Postgres because it brings great write throughput. But maybe you have this transaction, and later in the transaction in here, you do something that conflicts with an ongoing transaction, so then you still block. And now, while you're blocking the second transaction on the right, the first transaction is also holding on to the locks that it acquired in its first statement. Okay, but what happens if the first transaction then also tries to modify a transaction from the other, like a row from the other transaction? So they both modify the same rows, but in a different order. The transaction on the right holds on to locks on the rows where x equals to 2, and the transaction on the left holds on to locks on rows where x equals to 1. And now they're waiting on each other. There is no way out of this situation. There is no way to get both these transactions to commit because neither of them can continue. This is a deadlock. And the reason deadlocks are particularly bad is because not only do these two transactions get stuck, any new transaction that comes in and tries to acquire one of these locks that the previous transaction holds will also block. And maybe that blocked transaction will then block other transactions. So a deadlock can actually escalate into a full system outage if left unchecked, where all processes are blocked. Of course, Postgres has to solve this problem. Now, the way Postgres deals with this is, if a transaction is stuck waiting for a lock for more than a second, it runs a deadlock detection code. And the deadlock detection gathers the lock graph across all processes, the lock tables across all processes, and then builds a graph where each node is a transaction. So this is a transaction, this is a transaction. And the edge in this graph says this transaction is waiting for this other transaction. And then if there is a cycle in this graph, Postgres knows that there is a deadlock. When Postgres detects a deadlock, it cancels some of the transactions until that cycle is gone. In this case, Postgres might cancel one of the transactions performing the update, and then that ends the transaction. And then that means the canceled transaction locks are released. Then other transactions which are blocked waiting can now continue and finish. So one transaction dies and the other one lives. In Citus, we also support transactions. You can do a begin, update, update. But Citus delegates transactions to the node that actually stores your distributed tables shards. So here, for example, on the coordinator node, if you do two transaction blocks with updates in opposite orders, they get delegated to node 1. Then if those transactions create a deadlock, Postgres on node 1 will say, there's a cycle in this lock graph, I'm going to cancel one of the transactions. That sends back an error message to the coordinator will then abort the whole transaction. The other transactions that were blocked waiting can continue running. So okay, that works, but what if the transaction what if this transaction spans across multiple nodes? In this example, one of my rows in the second new example is on node 1, and there's another row on node 3. Transaction D1 is now waiting for D2 on node 1, and D2 is waiting for for D1 on node 3. The coordinator is just waiting to get a response for queries that is sent to these two nodes. And the Postgres on node 3 doesn't see a deadlock. The Postgres on node 1 doesn't have a deadlock. The coordinator doesn't have a deadlock. But if you look at the whole picture, there is a deadlock. So this is the situation we have to deal with in order to safely support distributed transactions. And what we did in Citus 7 is add a new component to Citus, which is the distributed deadlock detector. This component runs as a background worker as part of the extension framework. So this was the background workers that we started earlier on in our second talk. And if a distributed transaction gets stuck, it gathers all the log tables from all the nodes and then starts building a distributed transaction graph. And then so the distributed deadlock detector here in this box associates the transactions that go on node 1 and node 3 with the distributed transactions on the coordinator. And then the deadlock detector can say, oh, this distributed transaction is waiting for this other distributed transaction on node 3. Then it can perform deadlock detection on the graph, and it will see the cycle. The deadlock detector can then cancel the transaction on the coordinator, which will abort the transactions on node 1 and node 3 as well. And this way, other distributed transactions can continue. So this is necessary for implementing distributed transactions on a sharded database safely. In summary, distributed transactions are a complex topic. Most articles on this topic focus on the more visible problem around data consistency. These articles then discuss protocols such as 2PC, Paxos, or Raft. In practice, data consistency is only one side of the coin. On the other side of this coin is distributed deadlocks. And when your application runs concurrent transaction blocks that modify rows in different orders, you may run into a deadlock. If you want to scale out your relational database, distributed deadlock detection or avoidance is just as important as data consistency. With that, I'll wrap our third talk. And on to the conclusion. We talked about 3 technical problems today. First, replication and high availability in PostgreSQL. Second, PostgreSQL's extension APIs and how Citus leverages them to introduce distributed database functionality. And last, distributed deadlock detection. And the unifying theme across all of them was scaling out the relational database. I actually started out as a developer building against NoSQL databases. And there are actually good things to be said about NoSQL databases. I can see our VP of marketing getting stunned right here in the front row. We're like, wait, did he just say there are good things about NoSQL databases? What is he doing? Like, And the thing is, going back to the talk, when we started Citus, the database of choice among developers was NoSQL. So when we said Postgres, we'd often be dismissed as SQL doesn't scale. And the thing is, it's very easy to dismiss a seemingly intractable problem by making a statement that trivializes the problem. And the best way to solve a complex problem is not by dismissing the problem, but by breaking it up into smaller problems and solving them one by one. And we found at Citus that scaling out SQL isn't 1, but 8 different problems. In this talk, I talked about 3 of those challenges and how we approach to solving them. I hope you enjoyed learning about these 3 challenges, but if you'd still like me to simplify my conclusion to 1, not 3 takeaways, I say this. I learned this one thing through sweat, joy, and tears in the past 5 years. Scaling out SQL is a very, very, very hard, but not an impossible problem to solve. Thank you. Questions? We do have office hours after this one, and I'd be happy to chat about the 3 challenges in more detail, or the 5 other challenges that I haven't discussed after. I don't know how much time we have. I think about 1 or 2 more minutes. So if you have any questions, Like, I'm happy to answer them here or during the office hours.
How do you deal with the reliability with the coordinator nodes? Like, what if a coordinator node goes down?
So in the previous slide, and this was a simplified diagram. Give me 1 sec, I'll walk over it. But in the default and the simplified setup, the coordinator node also has a replica, like also has a streaming replication replica. So if it fails, then the replica for the coordinator node gets promoted. We do also have one advanced version of Citus, which most users don't need, but it's still available, where that distributed metadata can be replicated to all the nodes. That way, any node can become a coordinator node.
So if say you're looking for a solution for scale-up Postgres, right?
Mm-hmm.
We actually went to AWS conference earlier, and they announced they have the Aurora for Postgres, which can also scale up. So can you summarize, say, what's the difference between your solution versus the AWS Aurora? And okay, what's your kind of advantage over their solution?
So I'll give 2 answers to that question, because I think it's a two-folded answer. One is, obviously, Citus is open source, and it's available anywhere. So you're not locked into the AWS infrastructure. You can run it anywhere you choose. The second answer is more technical. What Aurora does is it takes the storage layer, and it scales the storage layer. So in here, if you look at this picture, and I'll go back, the volume, the persistent volume that you had, effectively becomes a way bigger volume that has better latency. And that enables you to scale the storage, so you can store more data. What Citus does is to go fully distributed, like in this picture, where you can talk to any one of the nodes. You scale not only storage, but memory and CPU. You can not only read, but write to any one of the nodes in the cluster, like in the MX offering. So that's the primary difference. Aurora approaches it more at the storage layer, and then Citus approaches it more at the database layer.
Actually, I read the post. It says, does that means, so AWS database, normally there are a few version behind of the open source version. So how about your solution?
So Aurora is, in those terms, is a fork of Postgres, where they actually fork from the core project and then they're rebasing. With Citus going into this extension method, because it's an extension to PostgreSQL, it basically, anything that's in PostgreSQL, whenever it comes out, is available to you at the time that it comes out. And any functionality in Postgres, by virtue of having leveraged these APIs, becomes available to the user without becoming a fork immediately. Does that answer your question? Yeah. Okay.
Say the HLL extension for Postgres? Oh, yeah. How does Citus work with other Postgres extensions? So, for example, like the hyperlog Postgres extension,
or timescale.
For the hyperlog extension, I can answer the question, and the default answer is 95 to 99% of the time it just works nicely. Because the way we hooked into the APIs is we paid attention, like what we need to hook in. Hyperlog extension is actually used by quite a few Citus customers, where they use the hyperlog log, or now there is a top-end extension to represent like approximate count listings. So you say create extension Citus, you say create extension hyperlog log on all the machines, and then they just happen to work together. Because we paid attention how we should hook into these APIs as we were designing them.